Okay, now that we have learned about the n-type and p-type materials, the charge carriers in these materials, the electrons and holes, and the way these carriers are actually moving across the semiconductor devices or the semiconductor materials or semiconductor crystals, let's actually make something useful out of this. If we join a p-type, as shown here, and an n-type material together, and this joining is not just by putting them physically side by side. There is some process involved. It could be done using a process called ion implantation or diffusion, or diffusion of dopants, or epitaxy. It's outside of the scope of our course, so we're not going to be really concerned about that. But let's say that we have joined the n-type and p-type materials somehow together. And if we do that, we actually made a device that, well, most of you probably have heard of it. It's called a diode. You might have actually seen the symbol of this device. It looks like this. Sometimes a triangle is actually a filled triangle, but it's a two-terminal device. We call this side the p-type side the cathode, and the n-type side the anode. Okay. We are going to talk about why the symbol looks like that. It's trying to actually show a certain direction and imply that basically this device or this element is actually a directional element, unlike resistors or capacitors that their symbols are kind of like symmetric. Doesn't matter from which direction you look at them. With diodes, we have some sort of a kind of a one direction kind of an element. Okay, we're going to talk about this device. We're going to call it for now PN junction, but we know that a PN junction is also called a diode. Okay, we're going to talk about this PN junction. We're going to talk about how like basically what happens when we actually join these two types of semiconductors, and we're going to talk about it in three different operation regions. These regions are called equilibrium, the reverse bias, and the forward bias. We're going to see how the voltage and current of this two-terminal element are going to be related to each other, and well, other things about this element. So up to now, we have learned that in an n-type material like this one, there are a lot more electrons than holes, right? So if I want to show with this line the density of electrons and density of holes, you can see that the Nn or N sub n, which is showing the concentration of electrons on the N side, is, well, sitting at a much higher level than the Pn, which is the concentration of holes on the N side, right? So you can think of the y-axis here being the density of charge carriers, right? So the higher you are, the higher density you're going to have, right? On the P side, things are exactly the opposite. So P sub P, which is basically concentration of holes on the P side, is sitting much higher than N sub P, which is concentration of electrons on the P side. Okay, so it's not a surprise that if I join these two types of materials to each other, what happens is that there's a big difference between the concentration of holes on the right side and the left side, and there's a big difference between the concentration of electrons on the left side and the right side. So this big difference means that the moment I join them, well, they're now one piece of crystal, right? So electrons and holes, theoretically, they could actually move this way or that way. So I know that from diffusion current, I know that when there's a big gradient in concentration level of certain carrier or certain charge carrier, like holes in this case, there's going to be a lot of holes moving from the p-type to the n-type. Similarly, I'm going to have a lot of electrons moving from the n-type side to the p-type. Okay. One thing that I want you guys to actually notice is that although electrons are actually moving from left to right, the current that is caused by this movement is actually from right to left, right? So this is the current of electrons, let's say, right, due to electron diffusion. And then for the holes are actually moving from right to left, and since they're positive carriers, the current is also going from right to left. So we have I holes from right to left. So this tells me that both of these currents are actually in the same direction, although the charge carriers are actually moving in the opposite directions. Okay, before seeing what happens to our PN junction due to these charge movements due to diffusion, we need to actually talk about a concept called charge neutrality. Let's say that I have this piece of crystal and it's an N-type semiconductor. And I ask you about, it's a crystal of N-type, so it means that it has a lot of silicon atoms and, well, a lot, but well, much smaller than the number of the silicon atoms. It has a fair amount of phosphorus atoms or any other group 5 kind of an element atoms. Now, if I ask you about the overall charge of this crystal, what do you think is going to be the overall charge? Is it going to be negative? Is it going to be positive? Or is it going to be 0? If you think about it, and I want you guys to pause and think about it, right? But if you think about it, you might actually, at first, you might actually answer that, well, the charge is actually probably negative. It's an N-type, so there are a lot of free electrons out there, right? But if you think about it a little bit more, you're gonna remember that it's true that I have a lot of free electrons here, but then each of these atoms, where do these free electrons come from? They come from these, well, phosphorus atoms, or they come from increasing temperature. But if you actually zoom in into each atom, let's say if I'm talking about a silicon atom, right? It has a nucleus, it has a bunch of shells, and then in the valence shell, it has 4 electrons, right? An atom by itself is charge neutral. What does it mean? It means that whatever negative charge all the electrons that are floating around the nucleus have in different shells, the exact equal amount of that charge with a positive polarity exists in the nucleus, right? So each atom, it doesn't matter what it is silicon or phosphorus or whatever else, right? Even like group 3 or any other group, right? So silicon, phosphorus, boron, or whatever else, we're going to have charge neutrality for each atom. So it doesn't matter if the electrons are actually free from the atom, free from the bonds of the atom, the covalent bonds or any other type of bonds that we have, or not. At the end of the day, if we count all the electrons, their total overall charge is going to be equal to the overall positive charge inside all the nucleus in all the different atoms, right? So it doesn't matter if it's an N-type, a P-type, or a pure silicon. The entire crystal is charge neutral. This is something that we need to remember before talking about what I'm going to talk about, okay? So in the beginning, let's go back to this diffusion current, right? In the beginning, at t equal to 0, I had this N-type material full of free electrons and this P-type material full of free holes, right? At t equal to t1, a few moments later, what happens is that we said a lot of these free holes are going to move to the N-type, N side, and then a lot of these free electrons are going to move from left to right to the P side. Okay, what happens if these movements occur? So when we have bunch of electrons, bunch of free electrons moving from the left to the right, what is left on the atoms what is left on the left side are some atoms that have 1 electron less than being charge neutral, meaning that we call these things in basic chemistry, if you remember, we call these things ions. So we're going to have some positive ions. And then we have a similar thing on the negative side, on the right side. So when free holes actually move from right to left, we're going to have some negative acceptor ions, okay? So the more movement I'm having from based on the diffusion and from right to left and left to right, the more of these ions I'm going to have, right? And if I just leave this crystal, this PN junction, be there for some time, for a fair amount of time, I'm going to have a region in the middle that is basically depleted of free charges. That's why we call it a depletion region. Okay, so on the right side I still have a p-type material. On the left side I'm going to have n-type material, but I'm claiming that at some point, or if I wait until like infinity, or if I wait long enough, this depletion region kind of is basically this diffusion currents are not going to be continuing indefinitely. There's a time that things kind of stop, and there's not going to be any more diffusion, and this depletion region is not going to be as wide as the entire crystal, right? So there's a limit, or it's basically it has a finite width inside the crystal, right? Let's talk about that. Let's talk about why and what basically is stopping our diffusion process. So once the depletion region is created, what we can notice is that I have this region with a net positive charge and this region with a net negative charge. From basic physics, we can actually remember that any particle or object carrying a net non-zero charge creates an electric field around it. So you can imagine that you can imagine why we're going to have an electric field here in this direction, right? From the positive to negative. What does this mean? It means that we have created a force that is now against the initial movements. Why? Well, with this electric field likes to actually push the positive charges from here to here. Let's show them with actual holes. So it's a force that it pushes holes to the right and electrons to the left, right? Initially, with the diffusion, my crystal or my PN junction like to actually move holes from right to left and electrons from left to right. But then this electric field is actually against that movement. So what happens is that once a depletion region is created, let's say first we have this layer of ions, and then we have the second layer, and then at some point, and then the more layers of ions I have, the stronger this electric field is going to get. So at some point, I'm going to have enough layers of ions that the electric field force is going to be equal to the force that is driving the diffusion. Therefore, basically, the holes want to diffuse from right to left, but the electric field's force is basically strong enough to drift them, or like basically to force them back to the right. And remember, the current or the movement of charges due to the force of an electric field, we know what's the name of it, right? We learned about it. It's called a drift current. So you can think about it that the holes want to actually do move from right to left, but then the same amount of holes are actually moved by the electric field from left to right. And at the point that we reach equilibrium, at the point that the depletion region stops from growing, is the point that these two forces become equal, these two currents become equal. Therefore, we can say that there's no net charge. There's no movement of charges from right to left or left to right in terms of the net movement. Okay? So when the PN junction reaches equilibrium, meaning that when the depletion region here stops from growing, and when we know that there's no carrier transport due to drift or diffusion because these currents are actually canceling each other, we can say with a good level of confidence, or pretty confident, we can say that the drift and diffusion currents due to holes and drift and diffusion currents of electrons are going to be equal to each other, meaning that, well, there's either no holes or moving from left to right or right to left, or if they are moving, the number of holes that are moving from right to left due to diffusion is equal to the number of holes that are moving from left to right due to drift. Okay, so the drift current and diffusion currents for holes and drift current and diffusion current for electrons are going to be exactly equal to each other. So let's see, what does that mean. So if I take the current density, the drift current density from the equation that we actually found in the previous slides, and make that equal to the diffusion current density, we have this equation. right? In this equation, we have Q on both sides, so I can actually cancel that out. And then I'm going to actually take an integral of both sides. So what happens is that, first of all, I take this P to the other side, put it in the denominator, and bring this dx from the denominator here to the left side. So I'm going to have mu P, which is a constant, comes out of the integral, E times dx, and I'm integrating over x. And on the right side, I have dP, the diffusivity, which is a constant, comes out of the integral, dP over P, and I'm integrating over P, the concentration of holes. Okay, so where do I go from here? Well, I know that from physics, I know that whenever I have an electric field over a crystal, if I integrate that electric field over dx from x1 to x2, I'm going to find a voltage. Actually, the voltage is going to be negative negative integral of x1 to x2 e dx. Okay, so I'm going to use that. So I have an e dx from x1 to x2. So this is going to give me negative mu p times, and then e dx is just going to be v, or, well, I brought the negative outside, so this is going to be just vx2 minus vx1. Okay, on the other side, I'm going to have, well, dp, and I know that 1 over p, integration of 1 over p is just going to be ln of p, so ln of p, which is basically from p sub n to p sub p, so this is going to be ln of p sub p minus ln of p sub n. Okay, so from here, I can just say that I'm going to bring this mu p to the other side, so this is going to be dp over mu p, and then the negative I'm going to multiply to the expression inside the bracket. So instead of vx2 minus vx1, I'm going to write vx1 minus vx2, and then ln of p sub p minus ln of p sub n is going to be ln of p sub p over p sub n. Okay, now if you remember the Einstein relation, we know that this dp over mu p, this fraction, is actually equal to kt over q. It's a constant, so this is the Boltzmann constant, this is temperature, and this is charge of an electron. And then ln of p sub p over p sub n, I can actually replace it with the actual concentration. So like I can say that I know that p sub p is going to be Na, so this is p sub p, and then p sub n is going to be Ni squared over Nd. So Nd comes to the numerator, so this is basically, this is the final form of our expression. Okay, so this V naught, by the way, is defined as Vx1 minus Vx2. So it tells me that when I have the depletion region and when I reach the equilibrium, I'm going to have basically a voltage across this depletion region, and the voltage I'm going to call it V naught, and this voltage is equal, it can be calculated using this expression. So what is the typical value for V naught? Let's say that, remember when we said that when we were doing doping, we said that the doping levels are generally between 10 to the power of 15 to 10 to the power of 17 atoms per centimeter squared. So let's go with the midpoint. Let's say that if Na is equal to 10 to the power of 16 and Nd is 10 to the power of 16, and we know that at room temperature, so T equal to 300 Kelvin, at room temperature, Kt over Q becomes equal to approximately equal to 26 millivolts. So this entire expression with these numbers, and we know that Ni for a silicon is equal to 10 to the power of 10 approximately, right? So with all these numbers, if you do the math, you're going to find V naught to be somewhere around 720 millivolts. Okay, So if you actually change these doping levels from 10 to the power of 15 all the way to 10 to the power of 17, you're going to see that a reasonable range for V0 is between 700 to 800 millivolts. And by reasonable, I mean in reasonable temperature with reasonable doping. We're not going to go much larger than 800 millivolts, and we're not going to be much smaller than 700 millivolts. So you can think of it that whenever a diode, a PN junction or a diode, is in the equilibrium, inside the diode, not across the diode, inside the diode there's a depletion region, and there's a voltage of 720 millivolts across this depletion region. So there's a barrier, there's this voltage across from Vx1 to Vx2. So basically Vx1 is greater than Vx2, and their difference is actually somewhere around 700 to 800 millivolts. Okay, this is something that we're going to use in analyzing all the diodes and in modeling diodes. This is a very useful piece of information.